Okay, in example 4, we're going to graph the periodic function, and we're going to apply it. So we have New York. In New York, we have Eldrick Park carousel, and it's known as the fastest carousel in the world. So it can go up to 18 miles per hour. The indoor court carousel is 50 meters in diameter. So draw a carousel. So it just spins around, right, 360 degrees, and that diameter is 50, right? And it can complete 10 rotations in a minute. So every 360 degrees it goes, it does 10 360s in 1 minute. So 10 rotations per 1 minute, right? The distance of a rider D from the front of a wall of the building varies periodically as a function of time. So they're just saying I can tell how far a person is away from the wall of a wall next to the carousel by having some type of like sine function or cosine function. So we want to identify the period of the function. So how long does it take to repeat itself? How long does it take to repeat itself? And then we want to graph that function. So it says some function of time. So that means I'm going to make a chart with time. And it says the distance of a rider of some point B. So say a rider's right here, and from the front of a wall. So we have some sort of wall here that rider is away from, and we want to find what that distance is in between here, right? So we have some time as he goes around here. At any point in any time, we can use a periodic function in order to see how far this person is away from that wall, okay? So we have time and distance away from the wall. So that's our two kind of variables here, time and distance. So we want to write some sort of function like y equals sine of t, or y equals cosine of t. Cosine of t. It's a little space there. So one of those two, right? That's what we want to identify the period. And once we can identify the period, then we can kind of graph it. And once we have the graph, then we can identify is it a sine function or a cosine function. So they give us a little bit more. They say assume the rider begins at a point closest to the wall 20 feet. So this is 20 feet to start. Okay. And so as they rotate around, well, how long would it take to just rotate once around? So we do 10 rotations every minute. So if I convert this and do for 1 minute is 60 seconds, then we can go ahead and cancel these out. And so 1/6 rotations per second. Or you can flip that and say 6 seconds with 1 rotation, right? So every 6 seconds we rotate 1 full rotation, okay? So in 6 seconds, our distance would be back at 20, right? And at 0 seconds when we start, it's a distance of 20. So what's happening in between? So if we rotate this to right here, what would the distance be? So that'd be 50 plus another 20, so that's 70. Well, how far is halfway? If it takes us 6 seconds to go all the way, what would be halfway? 3 seconds, right? Well, what if we split that? A quarter of a way, right? Wouldn't that just be right up here? Right there? And so that would be 1.5 seconds. And that distance, isn't that just from here to this edge right here, which would be 25, and then we can add 20, so that's 45. What if we went 3/4 the way around? Wouldn't that just be another 1.5 seconds added to this? So that'd be 4.5. And again, I am this distance, which is half of 50, because it's the radius, right, halfway in between. So 25 plus another 20 is back to 45. So we can see we have this rotation, and if we come back, we land right here at 6 seconds, and then go another 1.5 seconds. Again, we're at 45. So it's this repeating pattern of 20, 45, 70, 45, 20, 45, 70, and it just keeps on repeating that, right? So if we were to graph that, and maybe we'll put this down here, right there, and go 0, 1.5, 3, 4.5, more 6. We can say we can go to a 10, 20, 30, 30, maybe count. Yeah, let's do that. 10, 20, 30, 40, 50, 60, 70. 50, 60, 70, and graph this. We can see at 0 seconds we're at 20, at 1.5 we're at 45, 3 we're at 70, we reach its max, come back down, back to 45, and then back to 20. And then it just repeats this pattern, right? And it keeps going, and it keeps going. So which trig function does that look like? So if we look back, here is cosine. So notice at the beginning, cosine is kind of high, and then it drops down, right? Where on our graph, we start low and go up. And that's what sine does. It starts low and goes up. So we would say our function probably has to be a function of sine. And what's its period of the function? We can see that every 6 seconds, right here, 6 seconds, it has that same pattern from 20, 45, 70, 45, 20, and then again, this would be 45, right? It starts repeating. So our period length is every 6 seconds. So the period of the function is every 6 seconds. So every 6 seconds, it goes from 20, reaches its max at 70, and then comes back down to 20. And so we graph the function, we identified the period length, which is every 6 seconds. And so we've answered our two things. We want to identify the period of the function, which is every 6 seconds, and then we want to graph it, which we did. And now we can assume that it is a sine function, most likely. You could write it as a cosine function too, because if you just erase this part right here, now it looks like a cosine function, right? Starts high and drops down.